Okay, now let's talk about the hardware and the software involved in the PAC system. The heart of the system is the control computer or PAC server, which directs all the traffic. So you see the control computer sits right here. You have all the modalities down here. They talk to it through DICOM. You have the hospital information system, the radiology information system, and it will talk back and forth using DICOM work list. That's how it will communicate with all of these. And it also talks to the local area network and these workstations. So it's at the very heart. It speaks a language called DICOM, which we'll talk about in a minute. And it's the heart or guts of the system. The control computer uses magnetic or optical jukeboxes for data storage. The jukebox is a stack of 100 or more magnetic or optical disks, and it can store over 1 million images. From storage, images can be accessed to be printed, sent through a local area network. This is a network that is local. It is within your hospital system. It may go a little bit outside to a radiologist's workstation set up at home, but it's a part of a network that is local to the building, the local area. It may go to home. It's probably within one county if you want to think of it in geographic terms. It can also send through a wide area network. So if you have a patient that's being transferred from, say, LGH to CHOP, Children's Hospital of Philadelphia, you probably have a network connection between those two to share images. There's probably a lot of referrals from pediatrics to CHOP. So that would be an example of a wide area network where it's a primary network and you're sending data one time to be used at another location. So either local, inside Lancaster County, wide area network, outside it, going to different places like that. So the PACS control computer must interface with all different brands of medical equipment. Like I talked about, the control computer sits at the very heart. It talks to the HIS, the RIS, the acquisition workstations, everything. A standard high-level computer language was needed to make this work. So way back, before any of you were born probably, in the 80s, we had all these different systems, HIS, RIS, all these different types of modalities, GE, Philips. Nobody could talk to anybody. You couldn't make them work together. And so in the 1980s, a joint committee of the ACR and NEMA developed DICOM Standard. And it gave us the standard high-level computer language to be able to make them all work together. So the DICOM Standard stands for Digital Imaging and Communication in Medicine. It specifies only the transmission behavior of the various devices, not the specific architecture or terminology between different makes. And what that means is it is a transfer protocol. It is a image format, just like JPEG, bitmap, and things like that, but it's also a transmission protocol. And we'll talk about protocols a little bit later. So it determines how the two devices talk together, kind of like I talked about between the SCU and the SCP. It's the standard high-level language used to interface between all different brands of medical imaging equipment. DICOM commands. Don't get DICOM commands confused with DICOM functions. DICOM commands are go and do things, right? They involve actions. You're going to do a query. You're going to go find something. You're going to do a DICOM retrieve. You're going to go bring it back. You're going to send something. You're going to print something. You're going to get a work list. So when you think of a command, think of go and do. So don't get those confused with DICOM functions, which we'll talk about in a few minutes. Metadata. Metadata is extensive, detailed information stored behind the image for every image. It's data that gives information about other data. Okay? And so the metadata in an image is stored in the DICOM header. Right? And so key items of interest to caregivers are easily accessible by just clicking the button that opens the DICOM header. And it used to be, when we first started DICOM, a true header was actually displayed as a bar along the top of the image. We don't do that anymore. Now it's under a button. You click on the image. So the next 5 slides are going to show you key samples of metadata stored in an actual DICOM header. So notice that to the left, every DICOM data element has a DICOM tag ID. That's what I want you to notice. And also, you're going to see on the first slide that the accession number is one of the DICOM tags. And the accession number is the most important number in imaging. It is the one number to rule them all. So here you can see the DICOM tags, right? DICOM tag 0850. We typically don't read the leading zeros. If I was talking to another PACS admin, I'd say check 0850. And you can see that's the accession number, and there's the accession number for that particular study. It has the name, the patient ID, the body part. It has a lot of data. The ones in yellow are going to be most important to caregivers. KVP, relative X-ray exposure. So every image has all of these DICOM tag IDs with all of this information. Now I want to show you a real-life DICOM header from a real-life image. So here is a real-life DICOM header. And what I want you to notice about this is this section up here represents the DICOM header, and all of this that you can't read is that matrix of numbers that makes up the image. So the actual image starts below this line. This is all the actual image. This is the image pixel data. And up here is the DICOM header. Now right here would be the patient's name, but I've removed that field to anonymize this. But you can see other things. You can see what hospital this was done at. You can see what type of exam was done. Okay. You can see this is actually from a PACS gear unit. Some of this is human readable. You can make out some of the words and some of the things. You can see the provider's name is Dr. Michael Fitchett. So that's what it really looks like. If you open a DICOM file in Notepad, you will see that there's the DICOM header, and then you have all the pixel data. So another way to think of the DICOM header is consider this as a DICOM object. The bottle represents the DICOM container. The liquid inside the bottle represents the image pixel data. So the liquid corresponds to all of this down here. And the wrapper on the outside of the bottle corresponds to our DICOM header. We see that this DICOM object is a plain regular Coca-Cola. We know that because we can read the DICOM header. Uh-oh, this one doesn't have a DICOM header. How do we know what that is? Is that a regular Coke? Is that a Diet Coke? Coke Zero? Vanilla Coke? Cherry Coke? Vanilla Orange Coke? I don't know. I can't tell you what it is because I don't have the DICOM header. And that's not just for humans. Again, that would be for computers. When these DICOM files move around, the computers use the DICOM header to figure out what that image pixel data is. Without the DICOM header, the image is useless. I can't process it or use it in any way. And there's my DICOM header, so I can tell you that that is actually a Cherry Coke. And I'm going to have some image pixel data right now. Image pixel data tastes good. So, DICOM functions. Remember I talked about DICOM commands. These are go and do things. And a DICOM function, you just are manipulating things. So it allows the manipulation of the image. You can do window brightness and contrast, magnification, minification, but that's happening locally on the PC. You're not going and doing anything. You're just changing what happens at the PC at the local level of what you're doing right there. And so don't get your functions and your commands confused. Commands always involve verbs going and doing. So web-based PACS happens over the internet, and when you use web-based PACS over the internet, you're going to want to use encryption software to protect patient confidentiality. Image compression. Image compression comes in two varieties, lossy and lossless. Lossy is above 10.1 ratio of compression. It's called lossy because you're going to lose some of the image pixel data. Lossless is defined as less than 8.1, and it's called lossless because you don't lose any image pixel data when you do that type of compression. Image storage. There's limited capacity for workstations, right? So when you bring a study down, when you pull a study from PACS, it gets cached locally on the hard drive of your workstation. And that makes it easy to look at and view and manipulate. You're not having to do that over the connection to the PACS server. It just sends it down, and all that manipulation that we talked about a moment ago with DICOM functions happens with the computing power of the PC. So to make room for newly acquired studies, these things have to be erased. For CR, DR, CT, MR, nuke med, and ultrasound, it's usually 24 hours after acquisition. So you do these studies all day long, they get stored locally, and then overnight they get erased to make more room on the hard drive so that you can have the next day's studies there for post-processing and review. For quality assurance stations and radiologists' workstations, they usually stay 5 days in the cache and then they get erased. Again, this is so that images can be manipulated quickly using the computing power of the PC. Image storage. So within the PACS, it has its own type of storage that comes in two varieties. There's online or short-term storage, and this uses optical discs or tape media for any file recently accessed. So anything you did today and sent to PACS is going to be in online storage. Archive storage uses jukeboxes in a separate location. You want to separate your online and archive storage so that if one type of storage has a hardware failure, it doesn't affect the other. So you're going to put them in a different part of the data center or a different part of the building. So once studies sit around in online storage for a while, they're not being used, because once the image gets viewed, read, dictated, it's not going to be used until it's time to be used as a comparison. So it will sit there for a couple of days, maybe even a month, and then it will get archived off to the jukeboxes in the separate location. And last but not least, prefetching. During the night, the PACS system will look in the HIS and RIS and see who's coming in the next day, and it will go and find the comparison studies and pull them out of archive and put them down into the local systems, cache them on the radiologist workstations. Because you don't want the radiologist looking at today's chest x-ray, and he needs a comparison from last year, and having him wait 2 to 5 minutes for that to come out of the archive and all the way down to his workstation and come up. Radiologists, as you may or may not have noticed, are not the most patient people in the world. They're not going to be happy sitting there for 2 to 5 minutes waiting for these studies' prior images to come up. They want it all at the click of a button, and so that magic happens by prefetching. DICOM viewers. These are included on CDs and DVDs along with images sent to clinical sites. And it's real simple. There's DICOM 1.0, DICOM 2.0, and DICOM 3.0. There's 3 versions of DICOM out there. And so if we just sent the images on a CD and we burned them using DICOM 2.0, it probably wouldn't work if your hospital is using DICOM 1 or DICOM 3. So the best way to avoid those kinds of problems is to just include a viewer using whatever version of DICOM you use at your hospital onto your CD or DVD. Storage area networks. These protect against file loss from natural disasters. So don't confuse storage area networks with WANs and LANs. They're different. A storage area network isn't a primary network used for one-time image transmission. It's where you're going to store stuff long-term. It's the archive of the archive. So it's a subnetwork connecting several storage devices at a remote geographic location or other clinical site. So in the same way that we separated out nearline storage or short-term storage and long-term storage, we want a third storage area that's off-site, not even in the building. So if the building burns down by a fire or a flood or a volcano erupts, you're not going to lose all of your images. So you have a storage area network, or SAN, that all of these images get sent to, and they're stored away from the building so that it's safe and off-site. You don't want to lose all your images. Also note that SAN components are connected in parallel, so that if one component fails, the connections between the other components are not broken. So by parallel, we literally mean connecting them side by side in a rack. So you have this connection path where it can go between any of these. So if RAID 1 is down here at this point, if this connection is broken, the jukebox can still talk to the workgroup servers, RAID 2 or the workflow manager. So they're all connected side by side. And I know this was a really long video, and hopefully you didn't fall asleep, but I'll make the last one a little bit shorter. Stand by.